Hello everybody. My name is Maksat Jumamyradov. Just a little bit about myself. I'm doing my PhD in economics at University of South Florida. And today I'll primarily talk about, from the title of the presentation, you can see maximum simulated likelihood estimation of the mixed logit model. The title itself might look a little bit trickier for most of you. But my research primarily based on what's called discrete choice models. And it's an analysis of in general, what people demand, how people make their choices. So one unique specification of those discrete choice models is actually the mixed logit model. I'll show you why specifically we use discrete choice, the mixed logit model, because discrete choice models themselves you can think of it like a big umbrella of collection of models. A unique specification is the mixed logit model, and I'm primarily focusing my research on that specific model. And its estimation requires what's called maximum simulated likelihood estimation, and that's why I have it on the title. All right, what I'm going to do in this presentation, I'll first. Okay. All right. First, what I'm going to do in this presentation, I'll try to describe what discrete choice models are in general. Then I'll show you how one of the most commonly used discrete choice models, which is called multinomial logit model, is being derived. Then I'll switch to mixed logit model so that we can understand why exactly we need mixed logit model and why we cannot use multinomial logit model. Also, I will try to show you the estimation processes for both of them, multinomial logit model and mixed logit model. And I'll finish off with some results from the paper that my advisor and I published recently. Huh? Okay, all right. Is it better?
Yeah, that's great. That's good.
So I'm removing this one. Like double voice problem. Okay, all right. So far so good, or do you want me to explain it again? Okay. Okay. So whether you are aware or not, every single day, everybody throughout our lifetime makes some kind of choices. Some of those choices can be considered as insignificant. You probably don't even think about them. But some other choices have, like, you'll probably have to take your time. You'll probably make those choices only a few times throughout your lifetime, only a handful of times. So for example, I'm pretty sure everybody in this room had to decide whether they want to have some beverage in the morning. Then once you decide that you have a beverage in the morning, what type of beverage? Tea, coffee, or for example, when you commute to your work or to school, how are you going to commute there? Are you gonna just use a car or use some kind of public transportation or carpool? But some other choices you'll have to probably think more about. For example, if you have a job offers, multiple job offers, which one are you going to choose? In which city are you going to live? Or like, how do firms choose where to locate? If you want to buy some car, what alternative do you prefer? So what discrete choice models do, they primarily try to understand what people's preferences are. And based on that, we want to understand what is the demand, what's the market share for different alternatives. Understanding what the individual's preferences are will help, for example, governments in their policy-making procedures, or it will help companies, private companies, in their investment procedures, investment decisions. It's specifically called discrete choice models because the outcome variable is a discrete number or an integer. The researcher can only observe whether an alternative was chosen or not. Just to give you a clear example, the distinction between discrete and continuous choices, you can think about, for example, buying some gas. The decision whether you want to buy gas is a discrete choice. If you decide to buy it, it can be represented as like a binary choice model, 1. If you don't buy it, it's 0. But the amount of gas you want to buy is a continuous choice. And usually in discrete choice models, the outcome variable is being represented with just binary number. If you choose one alternative, it's 1. The alternatives that weren't chosen, which is 0. one of the first applications of discrete choice modeling was conducted in transportation. Researchers wanted to understand how people choose their destination locations and how people choose to get there to those destinations that they choose. To give you a more specific example, for example, if the state government wants to decide whether they want to invest in high-speed trains, they first need to understand if there's going to be enough demand for them to get back their revenue. If they how much fee they have to charge for the tickets. If they have to increase the taxes, by how much are they going to increase the taxes? So all those questions can be answered only after you understand the market in general, what people want. Another obvious application of discrete choice modeling is in marketing. What packaging people choose, what stores people usually go to, what kind of products or brands people choose. Understanding people's preferences in this kind of situation will help, for example, product company in their pricing process. How much are people willing to pay for the product that you are producing? For example, should you invest in advertising or not? Some successful companies out there don't even do any investment in advertising. They just rely on word of mouth. If you decide to do advertising investments, how much do you have to do? Another hot topic these days for the application of discrete choice modeling is energy sectors. If, for example, let's say government wants to encourage people to switch to renewable energy or to buy electric vehicles, they first need to understand what people actually want. How can we encourage people to switch to different types of renewable energies? But more relevant, I would say, and recently more popular application of discrete choice modeling is how people choose to get vaccinated. For example, this graphic you see is from my advisor's paper, Dr. Craig. You should remember around 2020 elections, there was this discussion of herd immunity. And CDC was saying that we need up to 75% vaccination uptake for the United States to get herd immunity level. So my advisor wanted to analyze that. So the question was, are we going to actually have enough people getting vaccinated for the United States to have that herd immunity, which is minimum 75%. Just to give you an idea about the timeline, if you remember, in December 2020, vaccines were available for only elderly people and children, as I remember, for doctors maybe, but for general public, it was only available around March 2021. So he conducted discrete choice experiments in November 2020. So he's kind of conducting these experiments to make a prediction about the future. He wanted to look what's going to be the vaccination uptake by the end of phase 2, which was August 2021, as I remember. So yeah, based on the discrete choice experiments that he conducted, just to give you an idea what discrete choice experiments are, you just ask hypothetical questions to people, and actually, I was one of those people who he asked questions to. So he asks hypothetical questions and simple question: which one would you prefer? And in this specific example, we have 3 vaccination types: vaccination A, B, C, and not to get vaccinated for 6-4 months. So we have different attributes. It depends on the researcher themselves, whatever they believe that plays a big factor in people's decision-making process. Those we call attributes. Some fields call them features. Well, for example, we have duration of immunity. If the immunity duration is too short, if it's shorter than 3 months, probably a lot of people will be discouraged from getting vaccinated. Or we have proof of vaccination. If you have to have kind of like vaccination ID card with you all the time, probably a lot of people will have to get vaccinated. Or we have settings of the vaccinations. Some people prefer medical settings because they feel more safe in there. There are like a lot of doctors in there, but some people are kind of like discouraged from that because they fear that there are already a lot of sick people in there, and there are long lines there. They will have to wait. So I might get another sickness from there. So they prefer like flu shots, for example. You can get flu shots in any other pharmacy in community settings. Risk of severe side effects, I think that's obvious, and vaccine effectiveness will probably play a big role in the decision-making process. So based on this kind of like questions, like you ask one question, hypothetical question, which one would you prefer? Then you change one of those attributes. You ask the same question again, which one would you prefer now? So like until we get an idea what people prefer. And he ended up predicting that by the end of phase 2, August 2021, vaccination uptake would be 68.81%. And he was right. I mean, when the numbers came, it was around 70%, which is way below than what we need for herd immunity. So this is just a perfect example of where we can use discrete choice experiments. We just want to understand what people's preferences are. And based on that, we can make different policies based on these or investments based on the analysis that we get. So predicted choice probabilities, we already saw how it's being applied. Like we can quantify future choice probabilities of people. That's one of the things that we can quantify by using discrete choice models. And another thing that we can quantify is called willingness to pay. If, for example, Apple company produced another iPhone, how much are you willing to pay for that? Or let's say if you could reduce your travel time by 30 minutes, how much are you willing to pay? Or if you have a computer which lasts for 8 hours, if you could increase that battery life for 2 more hours, how much are you willing to pay for that? We can quantify things like that using discrete choice models. Another thing that we can quantify is what's called price elasticity. There are 2 terms for that usually we use. One's called own price elasticity. If I have a company and if I produce something, if I reduce the price of the product that I'm producing, what's the change in the probability of customers choosing my product after the reduction in the prices? Or something called cross-price elasticity. If you take 2 competitors, for example, McDonald's and Burger King, if Burger King lower their prices, by how much percent the probability of McDonald's being chosen will decrease? So let's now talk about a short derivation of the commonly used discrete choice models. The theoretical basis of discrete choice models lay on what's called random utility maximization. So based on this theory, one of the assumptions is that every decision maker receives a certain amount of utility or satisfaction from different alternatives. And that utility is completely random from researchers' perspective. We have no idea what the utilities are. But from the decision maker's perspective, they know exactly what the utilities are. Another assumption is that decision makers are rational. So that means they will choose an alternative that provides them the highest utility. So from the researcher's perspective, we see that one alternative was chosen. We can automatically assume that that person chose that alternative because that alternative provides the highest utility for that person. We can formalize the utilities as equation 1. So the utility of individual I from choosing an alternative J. So I stands for individual and J for alternative, will be equal to some Dij, what we call deterministic part of utility. We call it deterministic because it's known by the researcher. We can observe, it's just the data that we have. Plus some stochastic part of utility, and that's where the randomness of utility is coming from. So as I mentioned earlier, utilities are completely random from researchers' perspective. The only thing that we observe is the outcome. And we call that outcome a variable y. So yij will be equal to 1, only if and only if that the alternative associated, utility associated with alternative j is the highest among the rest of the alternatives. And it's going to be 0 otherwise. So that's the only thing we observe. Alternative was chosen, it's 1. Alternatives that weren't chosen is 0. To mode 1, we can make only probabilistic interpretations based on this. So we can say that probability of yij being equal to 1 is equal to the probability of utility associated with alternative j being the highest among the rest. So that's first line of equation 2. And if we do the math and put everything together, we'll end up with the last equation, which is just the random part on one side of the equation and whatever we observe on the other side. And this looks like what's called, in economics at least, a cumulative distribution function. So based on the distributional function, we assume about the random part of utility, we will have different models. So there are 2 commonly used distributional assumptions for the error term, stochastic part of utility. One is normal distribution. And if we assume that we will get what's called multinomial product model. but my research is not based on that. So I just want you to know. The second part, if we assume that stochastic parts are independently and identically distributed, that's IID stands for, extreme value type 1 will end up having a multinomial logic model. The details are not that important as long as you know that we have two different distribution assumptions and we get two different models based on them. That's enough. The deterministic part, the data that we have, we usually in the literature assume that it's linear parameters. What that means is that it's just beta times x. We don't have like parabolic functions or beta. It's just beta times x. But the x part, we call them usually covariates. So it consists of the factors that will probably play a big factor in the decision-making process. And we can divide that into two. First part, we call them socioeconomic characteristics, or sometimes individual characteristics. Those are the things that are like specific to the individual themselves. Like, for example, your age, your education level, your income, your gender, etc. Like those kind of things will play a huge role in your decision making. Another part we call alternative attributes. Those things are the things that like specific to the alternatives themselves. It has nothing to do with the decision maker. It's the things like price, quality of the product that you choose, size, color, travel time, those kind of things. So like from different distributional assumptions, we get different models, and the multinomial logic model looks like this. So the probabilities that we derived previously, so it will be like probability of individual I choosing alternative J will have that nice functional form. Again, this is one of the most commonly used models in discrete choice modeling. The reason, like biggest reason is that its estimation is really simple. Like we use what's called multinomial logic model, maximum likelihood estimation, also related. But you just need to know that the estimation process is really simple. We don't have to do any kind of like simulations. One of the reasons is that we make really restrictive assumptions. And one of those restrictive assumptions is homogeneous preferences. What it means is that whatever preferences I have, we all have the same preferences. And you can see that in the equation, everybody have the same data. Whatever x they have, that might be different. But the multiplier, the coefficient we call beta, is same for everybody. It does not allow for individual specific unobserved factors. For example, you might take two people, which from outside looks like similar people, same income, same age, same gender, like preferences are same, but they choose different alternatives. We cannot explain that with multinomial logic model because it assumes homogeneous preferences. Another problem that this homogeneous preferences assumption leads to is called independence from irrelevant alternatives. Mathematically, what it means is that when you take a ratio of two different probabilities, two different alternatives, you will end up having that exponential function, which only depends on alternative J and M because we took a ratio based on those two alternatives. That's the mathematical aspect of it. Let me try to explain the intuition. So in the literature, usually that IIA property explained with red bus blue bus example. And assume, for example, you have 100 people and you give them two different choices. And for the sake of example, let's say 50% of them choose a car, 50% choose red bus. And based on the equation that we saw, that ratio cannot change if we assume homogeneous preferences. However, when we introduce third alternative, let's say blue bus, which is like the only difference between blue bus and red bus is its color. So it's like perfect substitutes to each other. And in reality, you will see some people switching from different alternatives to this blue bus. But the IIA problem says that if, for example, 25 people switch from red bus to blue bus, the same proportion of people have to switch from car to blue bus. And that's coming from the fact that when we take the ratios, it cannot change. The ratio of probabilities can't change. But that's not realistic. In reality, you will probably see that people who chose car will not switch to blue bus when they have that alternative, because blue bus and red bus are perfect substitutes to each other. What the IIA property ignores is that it assumes that every alternative in a choice situation is equally similar to each other, as it is equally dissimilar to each other. So assuming that blue bus, similarity between blue bus and red bus is the same as the similarity between blue bus and car is not realistic. So, like, to avoid those kind of unrealistic choice situations, unrealistic probabilities, we use what's called mixed logit model. Now, what this mixed logit model allows is that it allows individual specific unobserved heterogeneity. So whatever unobserved heterogeneity I have, it can be explained in the model. And usually in the literature, we involve that in the model by assuming that betas are not fixed anymore. If you remember from multi-normal logit model, it was same beta for everybody. But now we assume that beta is changing with individual I. And we assume that beta, usually in the literature, we assume that it's normally distributed with some mean and variance. And again, mixed logit model, it relaxes the homogeneous preferences assumption. And that's one of the biggest advantages of that. Now the estimation part. When we assume homogeneous preferences, it's really a restricted assumption. Usually in economics, like at least in economics, researchers assume really restricted assumptions to make the estimation process simple. So you have this trade-off, like, do you want to make your model more realistic? But in that case, you'll have to make the estimation process more difficult. And that's exactly what's happening here. When we have multi-normal model, we have really restricted homogeneous preference assumption, but that helps us to have really simple estimation process, which we call the maximum likelihood. So you can think of that function as choice probabilities we just saw. So the only thing you need to do is take the first derivative, equalize that to 0, and find the parameters that maximize that likelihood function. But when we have this latent variable in the choice probabilities, latency is coming from the fact that we assume that beta i's are individual specific. We cannot put that into the likelihood function anymore because researchers don't know what that is. And we cannot move on by taking the derivatives and find the parameters that maximize the likelihood function. So what we do, we use what's called maximum simulated likelihood. The only difference is that we now have to simulate the likelihoods based on the distributional assumptions we make. So we take number of draws from like samples from distribution, put that into the likelihood function, and that UIS is that like draws that we make. And we do the same procedure as we do for the maximum likelihood, but we do that over and over and over again, not just once. And then after all, we just end up taking the average of all. So now, let me try to explain the motivation. I'll explain the paper that my advisor and I published recently. It's closely related to the maximum simulated likelihood estimation, and it's indirectly related to the mixed logit model. So in the mixed logit model, researchers mostly will assume that the random coefficients, beta i's, are normally distributed. So we wanted to separately analyze that normal model, separate that from mixed logit model, and analyze separately. One of the advantages of that is that we can estimate the normal model using both of these estimators. By doing that, we can directly compare the performances of different estimators. So if there's any differences in their estimation, the results that we get, we can pinpoint and say that, oh, there is a problem in the maximum simulated likelihood estimation. Because theoretically, we already know that maximum likelihood estimation is unbiased estimated. But we also know that there is some kind of simulation bias coming from the simulating the likelihoods, but we don't know by how much that affects our estimation results. So that was the reasoning behind why we wanted to look at that paper that we're about to present. So biases in the maximum simulated likelihood estimation of bivariate models. We looked at two different models, bivariate normal and bivariate cosine. So again, bivariate normal, we can estimate the same exact model. We just need to rewrite it with maximum likelihood and maximum simulated likelihood. That allows us to directly compare the performances of two different estimations. Just a quick explanation of what type of models we have. Bivariate normal model that y1i and y2i is distributed bivariate normally. We have intercept, we call them intercepts alpha 1. Betas are random, just like in the mixed logit model. And we have covariance matrix of the error terms normally distributed. We have a correlation sigma rho. We have variances for each of the random variables. And what we do is just we try to estimate these parameters. So notice that we can write the betas, random betas, as like we can separate from mean, like beta 1 and beta 2 are mean, and the disturbances are u in the last equation that we see. That will allow us to estimate the same exact model with two different estimation methods. So we have to estimate this using maximum simulator. This is exactly the same model. The only thing we do, we take the x times u's, if you remember from last equation, and we put them into the error terms. Now the error terms are not epsilons, it's just v. Functional form of v is the equation that we see. We can estimate this with maximum method. So two different estimation methods, same exact model, the same parameters that we generate. So first, this is the results that we get from maximum likelihood estimation of the bivariate normal model. We generated the data with alpha and beta. Alpha is -1, beta +1, with three different variances. And in this table, the correlation parameter that we generated the data with is 0.96. And as you can see from the results, we can pretty much estimate all the parameters that you see on the table. But we specifically focused on the correlations. If you see the correlations, the estimated values for three different variances are really close to the true correlation up here. Another thing I want to mention is that for this simulation study, the paper, by the way, is purely Monte Carlo simulation study. We did like 200 simulations and 200 estimations. To be able to do that, like we used what's called, in the estimation process, we used parallel computing. So like if we wanted to do that with regular 8-gram computer, it would have taken us so long. But even with the parallel computing, it took us a little less than a day. Not the maximum likelihood estimation because it's simple, but the maximum likelihood estimation took us so long. So again, as you can see, we can estimate all the parameters that you can see on the table, correlations, three different sigmas, alphas and betas, really close to the true values. But now we have maximum simulated likelihood estimation of the same exact model. The only thing we do, we just rewrite the model. True value of correlations, 0.96, but we estimated when the variances are 0.25, we're estimating the correlation to be 0.6. It gets closer when we improve the variances, but still, there is huge difference from their true values. Same happens for three different graphs. Just to give you an idea of how big those are. If you remember in the simulation of likelihoods, we have to take samples from distribution, but there are different techniques of taking samples. Halpin draws is just one of the techniques that we do. And we took different numbers of samples. We took 250, 500,000 rows, and we estimated the same exact or the same model over and over again. What I do here in the table too, for example, we have only one correlation parameter, 0.96. But what we did, we looked at the range of the correlation parameters, starting from 0.96 all the way down to -0.96. With increments of 0.03. So it's like we generate and estimate the model with correlation being 0.96, then we move and do the exact same thing with correlation being 0.92, 0.88, like with increments of 0.04. And we graphed all the estimates of correlations for the maximum likelihood estimation. And here the results. So on the horizontal axis, we have true values. On the vertical axis, we have estimated values. On the diagonal, we have a black line, which represents the true values. If you're close to that little black line, it means that you can pretty much estimate all the correlation values that we have. And as you can see from the graph, the three different lines, which represents three different variances that we chose, are pretty much on top of each other. So it means that we can estimate every parameter, right? All the correlations, no matter if we have high correlation or low correlation, doesn't matter. But now let's see what's happening with maximum simulated likelihood. Now we cannot estimate the correlations, especially when we have really small variances. So from this, we can say that although we use the same exact model, we only rewrite it in a different way, so that we need to have, like, we need to estimate in two different estimators. Maximum likelihood estimation does a pretty good job for maximum similarity likelihood cannot estimate correlations. So when correlations are high, either positive or negative, and especially when the variances are really low, we cannot estimate the correlation values. But when we increase the variances, it seems like, for example, when the variances are 1, we can estimate the correlations. So what we wanted to do in this little study, since mixed motion model is commonly used in discrete choice model, and for its estimation, we have to use maximum similarity likelihood. We just wanted to say to the researchers, be careful in your estimation processes. You might not be estimating the things that you want to estimate. And like, as I mentioned earlier, we also did bivariate Poisson models. We use Poisson models for count variables. For example, let's say if you're suspecting that the number of doctor visits is correlated with the number of days you stay in a hospital, you can use bivariate Poisson. Or for example, let's say the number of firms entering the market will be correlated with the number of firms exiting the market. So you can use count variables for that. You can use bivariate Poisson. So the same idea, we generated the correlations with, just like we did for the normal model. All the estimates were supposed to be like really close to the black line, but as you can see, we have really weird sigmoid shape for the estimated correlations. So this is pretty much it for my presentation. Thank you very much. If you have any questions, feel free to ask.
Tamam maksat sorular var mı? Online platformlarımızda sorular varsa.
So do our extended warranty scam companies use this logit model?
Auto scam, what?
Do the our extended warranty scam companies use this logit model?
I can say that pretty much like a lot of companies that like work with the customers and try to understand their purpose. Pretty much every company that work with like trying to like understand people's preferences, they use some form of discrete choice models. There are many types, depending on the specification that you use, or depending on what researchers want to estimate. You can have different specifications of discrete choice models. But I can say that like pretty much every company uses them. Or if they don't use directly, they go to the consulting firms and get their help. There's a question over there. All right.
Relegated.
Height modelleri bir tane height slide. Aha.
Ondan sonra survey'ler dedim şu survey'den datalara göre düşünüşüne göre sonra parametre fit edemez. Ondan sonra fit edemez de overfitting ya underfitting problemler var yani.
Edelo discrete choice experiment like nemede onyali problemi bolmany üçün yardım şuna göre şu paper'ımı ödünden onyali da o arada gıdıklanmanı üçün ya either he just ignored it, but yes, we might have overfitting or underfitting issues, but it's not that common in discrete choice experiments, at least. Yeah.
In case of outliers in data set, would it be better to use SVM than logit model?
To be honest, outliers, it depends. Like it just complicates the model. Some researchers prefer just ignore them. Of course, if the estimate, it does not affect the estimation models, estimation results that much. But some researchers prefer just to ignore them because it overcomplicates the model estimation processes, especially if there are only a couple of outliers. Personally, I would just suggest to ignore them.
Endi so'roq.
It says, why can't we use mean square error as a cost function for logistic regression?
It's not a cost function. We're just trying to predict the choice probabilities of different alternatives being chosen, and especially for disaggregate level, which means that individual specific. Because usually a lot of analysis do in general, like average level, but the advantage of the mixed logit model, at least, is that we can allow individual specific heterogeneity in the model. With mean squares, we cannot do that.
Başka soru var mı? Auditoriyamızda, online platformlarımızda. Maksat mende soruğı var. Şimdi şunları metotları, aynı Amerika'da bir content üreten bir elections'ta olan koyuyor.
Yeah, choice probability of. As I mentioned earlier, in any situation where you want to predict choice probabilities of two different alternatives, that alternative can be like you go to grocery shopping and want to choose different milk, or like even in the election, like two different alternatives, Democrats, Republicans. It's just that you just need to change the question in there, like, but the idea is the same. Two different alternatives, and each individual choose based on whatever preferences they have. Yeah.
Soru.
Çaydan sonra Q&A'dan.
Yine de bir soru. So the assumption is that people are rational actors. Do the expected outcomes differ since in real life people don't always act rationally? Is there a method to account for that difference at all, or is it an assumed risk?
Without assuming that individuals are rational, we can't even move on from that point because we need to make probabilistic interpretations, and that depends on assuming that people are making rational decisions. Economics 101, we always assume that people are rational. So yeah, like without that assumption, we cannot do the analysis that we do.
Başka soru var mı?
Okay.
Maksat köp sağ ol. Tanrı arkasın.